Okay, so for this question, we have a hoop or a wheel rolling down a ramp, and we wanted to sort of describe what's going on. So our first step is to draw a free body diagram. So I'll kind of reproduce that. If I can, right, roughly like that. And we're told that this point at the center, and that's the center of mass of the wheel and also just the actual physical center. And so this problem is tricky not because of what you have to do, but how precisely you have to answer it. Right? So it's a long sort of paragraph here of text. We have to draw and label the forces, not the components of the forces, but the forces themselves, that act on the wheel. And we need to indicate at which point the force acts by showing that's where we start the arrow. So we can't just draw the arrows all coming from the center of mass because that's not where all the interactions happen. So we have to be a bit more detailed. So the first step, the simplest force in my mind, is to talk about gravity. And gravity always acts at the center of mass. That's something we talked about when we talked about gravity in chapter 5 or so, and when we redid rotation in chapter 7, 8, something like that. Gravity acts at the center of mass, and gravity is always vertically downward. Right? So this could be the weight, you could write mg, you could write the force of gravity, whatever that might be, but it starts at the center of mass. So that's force number one. We know the wheel does not fall through the plane. That tells us there must be a force from the inclined plane on the wheel, the normal force. And the normal force is perpendicular to the surface, and it acts at the point of contact, which is where the wheel touches, right? So like there. And then finally, we're told the ramp exerts a force of static friction on the wheel. So the static friction force is always parallel to the ramp surface. So the only question we have to determine is, does it point up the ramp or down the ramp? And the answer is that it is up the ramp because that's sort of the direction that it would roll in, right? We know from sort of everyday experience that it's going to need to start rolling kind of like that way as it goes down the ramp. And that means we need well, I'm kind of answering part 2 with this, but the only way that happens is if friction prevents it from sliding this way, right? Without friction, it would just slide. Let me change that color a bit, right? Without friction, it would just slide kind of on that path. It wouldn't start rotating it at all. And so friction has to prevent that kind of motion, the blue arrow. And so that tells us that friction has to point up the ramp. Right, something like that. Okay. So those are our 3 forces. And you notice how I've been very, very clear about how they draw and where they start, the direction they point in. And so this free body diagram will help us answer part 2, and I've already kind of done it. So the question is, which force causes a change in the angular velocity of the wheel? Well, we have 3 options: the normal force, the weight, and the force of friction. And there's a couple different ways you can look at this explanation. The first is a purely descriptive one. If there was no friction, would the wheel rotate? And the answer to that is no, it wouldn't. Friction must be the thing that causes it to rotate, because everything else is what makes it go down the ramp, right? So rotation happens only because of friction. The more mathematical and precise way is to remember we're looking for something that causes a change in angular velocity. And we have to remember that this is related to an angular acceleration alpha. And we know that angular acceleration is related to a net torque, right? This is the tau equals I alpha equation, the Newton's law in rotational form. And so if we can figure out what force exerts a torque, then we can figure out which one causes an angular acceleration, and therefore which one changes the angular velocity. So we're going to calculate these kind of turn by turn. The torque due to the weight is the weight force. Actually, let me back up. So in general, right, the torque is RF times the sine of the angle between the two. So for the weight, R is drawn from the center of mass to, the pivot point, which in this case is the center of mass, to where the force is applied. So since the weight is applied right at the pivot point, R is 0. The weight is mg, and sine theta doesn't really have a lot of meaning, so it's the same exact point. So this is 0. The weight force exerts no torque mathematically. Therefore, it cannot cause the change in angular velocity. What about the normal force? Well, the normal force doesn't act at the center of mass, so R is, I'm going to call it capital R to differentiate. It's the radius of the wheel, right? R. The normal force, I'm just going to write it as n for now. It's not 0, definitely. However, when we write sine theta, that angle is going to be 180 degrees. Right, because R points along this line, and the normal force points along that line too. They're parallel, or anti-parallel, I guess. But either case, the sine of 180 degrees is 0, so that is 0. So finally, we come to friction. The torque due to friction, once again, it's the center to edge distance, the radius, the force, and now we see that friction acts at a 90-degree angle, right? That sort of shape. So this is R times FF, right? Because sine of 90 degrees is 1. And that is not 0. So because this torque is not 0, we have a net torque, which leads to the angular acceleration, which leads to a change in angular velocity. So friction is the only force that causes the torque, therefore it's the only force that changes the angular velocity. Right, and again, this is kind of a little bit overkill for this question, but it shows the details that you can think about. You can write this entirely in words. The goal is to somehow explain that friction is the only force that causes a torque. All right, and finally, part B, not finally, part B. This is another one where the wording is kind of difficult. So we want the linear acceleration, and we're describing forces. So the equation that comes to mind when I think I'm trying to answer a question about linear acceleration, and I'm given information about forces, is to use F equals ma. So, this is F net. So what we need to do is go back to our free body diagram, and now we're not talking about rotation, we're talking about net force. And we only care about the up the ramp and the down the ramp part, because it's not going to move sort of into the ramp and off the ground of the ramp. So what forces do we have that point up the ramp or down the ramp, or components of that? Well, that one points up the ramp, and a part of the weight is going to point down the ramp, right? That's theta, and so this is W sine theta, right? So W sine theta points down the ramp, the force of friction points up. And that tells us the net force. We're going to move down the ramp, so I'm going to call that the positive direction. So the weight, mg sine theta, minus the force of friction equals ma. So this is nice, but we're told something about the force of friction. We cannot write this is mu times n. And we can't do that because we're told that the magnitude of static friction is not the maximum. We're told that it's 40% of the force that's directed opposite the force of friction. Well, what force is directed opposite that of friction? This component. So the force of friction has to equal 0.4 mg sine theta, right? That's what that means. This is 40% of the force directed opposite. So mg sine theta minus 0.4 mg sine theta is 0.6 mg sine theta, and that still equals ma. Now we can cancel the masses, and a equals 0.6 g sine theta. Right? And so the trick in this one is really this piece, right? Recognizing what that means. If you've drawn the good free body diagram, it's easy to find what force is opposite that of friction, and then translating that into math. But that's, I think, the challenge of that problem. All right, and finally now, part C. We repeat the experiment with a block of ice, and instead of something rolling, it just slides, but there's no friction anymore. So which one reaches the bottom with the greatest speed? Well, there's two ways you can kind of come at this. I think the easiest one is to compare the accelerations. or rather the forces. So the free body diagram for the block, that's a terrible, terrible block, right, is going to look like this. And the wheel we already drew. So the F in the down ramp direction is mg sine theta here, and for the wheel it's mg sine theta minus ff. So their masses are the same. So this one, right, this is a bigger force, net force, than that. So bigger force for block. If we have a bigger force, we have a bigger acceleration. If we have a bigger acceleration, then we travel faster, right? Because we know this distance is the same, so we would be able to calculate the V final, right, using this one. Right? If this goes up and this stays the same, and that's 0 in both, then V final must be bigger for the block than the wheel. So the block reaches moving faster. Right, so that's in terms of forces. Now in terms of energy, this is the other way to approach this question. In terms of energy, we have a certain amount of gravitational potential energy available, right? That's the mgh available. The block converts all of that to rotational kinetic energy. The wheel converts it to three things: rotational, translational, and thermal energy. That's kind of hidden on the side. And so since this is a much sort of cleaner conversion, this one will end up with the larger translational kinetic energy, right? And therefore the larger velocity. So the block is true in either way.